Alright, chapter 3 for grade 8, Pythagorean relationship. In this chapter we've got 3.1 squares and square roots, 3.2 is exploring the Pythagorean relationship, 3.3 is estimating square roots, then there may be an assignment, 3.4 is using the theorem, 3.5 is applying the theorem, there may be another assignment, and then we'll wrap up the chapter with our exam. So, for today, 3.1, squares and square roots, identifying perfect squares. So, we're starting with, we'll deal with something called prime factorization. And we need to determine the prime factorization for 24, 36, and 81. So, the prime factorization, as a definition, is a number written as the product of its prime factors. So, for example, the number 12 can be written as 2 times 2 times 3. These are all prime numbers, and so this is the prime factorization for 12. So for 24, we can do the prime factorization for that. And the way to do this is you can start with a factor tree. And two numbers that multiply together to make 24, let's say 3 times 8. Now, any pairing will work for this, except for 1 and 24. That won't get you anywhere. So any factors that multiply together to give you 24 will work. Now, the number 3 is prime already, and prime means that it is only divisible by 1 in itself. It has no other factors. So 3 is prime, so I'm going to circle that. 8 is not prime. It can be divided into the pairing of 2 and 4. 2 times 4 gives you 8. Now 2 is prime, so I'm going to circle that. But 4 is not. It can be broken down further into 2 times 2. So the numbers that I have circled here multiply together give you the prime factorization for 24. So 3 times 2 is 6, times 2 is 12, times 2 is 24. So that is your prime factorization of 24. So that's the solution for 24. Now for 36, again, break it into a pair of factors that multiply together to make 36. And let's go with 4 and 9. 4 times 9 gives you 36. Neither of these are prime. So 4 can be broken into 2 times 2, which those are both prime. So I'll circle those. And then 9 can be broken into 3 and 3. 3 is prime, so we've gone as far as we can there as well. So 2 times 2 times 3 times 3, that gives you 36. So that is your prime factorization for that. And lastly, let's do 81. 81 can be broken into 9 times 9. As we saw before, that's not prime. Each one of those can be broken into 3 times 3. 3 is prime, so I'm going to circle those. That's as far as those branches can go in this tree. And so then we know that 3 times 3 times 3 times 3 is the prime factorization for 81. So that's the process for figuring out the prime factorization. Part B, which of the numbers is a perfect square? Now, a perfect square can be illustrated as being the area of a square. Like we've got over here, we've got a square drawn out. So its area is a number that is a perfect square. Now some examples of perfect squares. 1 squared, which is also written as 1 times 1, is just 1. That one is not an outstanding example, but it is true. 3 squared is 3 times 3, which we know is 9. 9 is a perfect square. 2 times 2 gives you 4, so 4 is a perfect square. 4 times 4 is 16, so that is a perfect square. Now, if you're calculating the area of a square is equal to its side length squared, or S times S. So in this case, if we've got 4 by 4 on a square, then we know its area is 16. So 16 is a perfect square. So, a few more examples of perfect squares. Well, let's look at a few. If you've got a square that's 3 by 3, it's 9, as was illustrated up there. If you've got a square that is 5 by 5, then the area is 25, and so 25 is a perfect square. Do a few more examples. If you've got a 6 by 6, its area is 36, so it's perfect square. We'll do 8 and 8. Those work out to be 64. You could do a square that's 10 by 10, and it would be an area of 100, so 100 is a perfect square as well. So all of those are examples of perfect squares. There's an unlimited possibility of numbers that are perfect squares. Any number multiplied by itself, the answer you get is a perfect square. So, based on that information, we've got a show you know, please go ahead and try it out.